In this video, let's look at sort of the inverse trig functions, hyperbolic trig functions, and we're going to look at the derivatives of those functions closely. So let's go over first the derivatives. The derivatives of the complex trig functions. Okay, so recall in the last video, recall that by definition, sine of z, this equals to e to the iz minus e to the minus iz divided by 2I, right? And then cosine of z is equals to e to the iz plus e to the minus iz over 2, right? Those are the definitions of sine and then cosine respectively, right? So if we want to differentiate sine of z, well, all we have to do is just use the sum and difference of derivatives rules you've seen in calculus, right? So really, we're going to differentiate a sum or a difference of two functions, e to the iz minus e to the minus iz over 2I, right? So this would equal to, I times e to the iz. This will be a plus I e to the iz over 2I, right? The i's will cancel here, here, and on the bottom. And so we'll have e to the iz plus e to the minus iz over 2, which is exactly cosine of z, right? So the derivative of sine of z is cosine of z, right? Okay. And we know this function is entire on the complex plane, right? E to the z and then sine of z. Also cosine of z, we'll show that in a second. And then all polynomials are entire. So this is pretty powerful. So they're differentiable everywhere on the complex plane. So if I want to differentiate cosine of z, well, all we just do is apply this differentiation rule to these different sums of two functions, e to minus iz over 2, right? So this equals to I times e to the iz minus I times e to the iz divided by 2. Okay, so this equals to, so I'm going to do I e to the iz minus e to the minus iz over 2. Okay. And if I multiply the numerator and denominator by I, what this is going to look like is, so I'll have a minus 1. I squared is negative 1. So I'll have e to the iz minus e to the minus iz over 2I. Okay. Which is minus sine of z. Okay. So what do we know? The derivative of cosine of z is equal to negative sine of z. Okay. And also these other derivative rules you've seen in calculus. The derivative of tangent of z, this will equal to secant squared of z. Okay. The derivative of ordinary secant of z is equals to secant z tan z. Okay. The derivative of cosecant is equals to minus cosecant of z cotangent of z. And the derivative of cotangent minus cosecant squared of z. Okay, always cosecant of z. All right. So these would be, along with this one, the derivative rules for trigonometric values for complex numbers. Okay, so pretty straightforward. What I want to talk about next are the inverse trig functions. Okay, inverse trig functions is next. So the goal here, so if W and Z are complex numbers, we need to show a relationship for this equation. So we want to figure out what W is equal to. If W is equal to inverse sine of Z. So in other words, we want to figure out a Z in the W plane in the Z plane such that inverse sine of Z is equal to W, right? So to figure out what Z has to equal to, well, what this means is that Z has to equal to sine of W, right? Sine of W. Okay. So by definition of the sine function, Z is equal to e to the IW minus e to the minus IW over 2i. And then we're going to come up with a polynomial in terms of e to the IW. So if we multiply both sides by 2i here, right? So what's going to happen is we'll have so z 2iz is equal to e to the IW minus e to the minus IW. Okay. And also, if we multiply both sides by e to the IW, well, we'll have so 2iz e to the IW equals to e to the 2iw minus e to the IW minus 1, excuse me. Minus 1. Okay, minus 1. All right. So if we add the left term to both sides, we'll have a quadratic equation in terms of e to the IW. So we'll have e to the 2iw, e to the 2iw minus 2iz e to the IW minus 1 equals 0. Okay. And if I do a proper u substitution by letting u equals e to the IW, in terms of u, this equals to u squared minus 2iz times u minus 1 equals 0. So this here is a quadratic equation. Quadratic equation in terms of the complex numbers, right? So we're going to use the quadratic formula. And so I should say a times z squared. Let's be z plus z is 0. A, B, C are complex numbers, and A is not the 0 complex number, right? So z is equal to minus b plus the square root of, actually, I'm going to write it like this. B squared minus 4ac to the 1/2 power over 2a. Notice here is we have a plus sign here because in the complex quadratic formula, this quantity here would be a complex number. And with complex roots, right, this will incorporate two distinct complex roots, right? So we don't necessarily need the plus or minus symbol in the middle here, okay? That only constitutes with real numbers, right? But in complex numbers, we just omit the plus or minus symbol here in the middle, okay? Because this quantity here as a whole would give us the two distinct roots that we need, all right? So this here is the quadratic formula for complex numbers. It looks exactly the same, right? So we're going to use that here. So in U, this would be U is equal to 2iz plus the square, well, essentially the quantity minus 2iz squared minus 4 times a, which is 1, and c is -1, to the 1/2 over 2 times 1, okay? So u is 2iz plus, this is, so I squared is -1, so that is 4z squared. Okay, I gotta be careful here. So I squared -1, okay. Yeah, okay, I'm on the right track. All right, so minus 4a and c. Okay, so yeah, okay, so I'm on the right, yeah. Uh, minus 4a right, okay. I just gotta check to make sure. So minus 2iz is minus b plus or minus 2 squared 4. Okay, so minus 4z squared. Yeah, so that's minus 4z squared plus 4 to 1/2 power over 2. And if I reduce this down, I'm on the right track. So 2iz. So this would be plus 2 times, I'm going to write this out as 1 minus z squared to the 1/2 over 2. And so u is equal to iz plus literally the square root of 1 minus z squared. And that's it. Okay. We need to take note that u is equal to e to the iw. So e to the iw is equal to I times z plus 1 minus z squared to the 1/2 power. And if we take the logarithm of the both sides, so we'll have I times w equals to the natural log of iz plus 1 minus z squared to the 1/2 power. And so w would equal to the natural log of that quantity divided by I, but we have to multiply the numerator and the denominator by the complex conjugate of I, which is minus I. So you'll have minus I times the natural log of iz plus the square root of 1 minus z squared. Okay. So that would be the inverse of sine of z. Okay. Inverse of sine of z. So here is also the inverse functions for cosine of z and tangent of z. Okay, so you can do this same thing. So, okay. So inverse sine of z is minus I times the natural log of iz plus 1 minus z squared to the 1/2 power. Inverse cosine, this is equal to minus I times natural log of z plus I times 1 minus z squared to the 1/2 power. And tangent, inverse tangent of z, or arctangent of z, which equals to I over 2 times the natural log of I plus z over I minus z. Okay. These will be the inverse functions to worry about. Now, in order for an inverse function to exist, we need to have a well-defined function. So we need to restrict the domains for the natural log and the square root function. So usually they will, in the textbook, in your problem set, your problems indicate you want to use the principal branch for the logarithm, and they will give you some branch in the square root function. Usually it's the principal branch for the square root function, right? So the principal branch, so the principal branch for z to 1/2, this is where theta is in between minus pi over 2 and pi over 2. And the principal branch for, in this case, the logarithm is in between minus pi and pi. So take note of these. You might use those in future problems. So also the derivatives. the derivatives of inverse trig functions. So the partial, the derivative of, with respect to z, of inverse sine of z is equals to 1 over 1 minus z squared to the 1/2 power. The derivative of inverse cosine of z is equals to -1 divided by 1 minus z squared to the 1/2 power. And the derivative of the tangent function, inverse tangent, which is equal to 1 divided by the square root of 1 plus z squared. Okay, I'm sorry, it's 1 plus z squared. 1 plus z squared. Okay. Yeah, so in order for an inverse function to exist, they need to be defined on some specific branch cut, right? So for context, you could use the principal branch of the square root function, right? Which has length 2 pi. And then for the logarithm, you want to use the principal branch for the logarithm z, which is this range here. Okay, so to show the proof of these derivatives of the inverse functions, it goes back to implicit differentiation, right? Implicit differentiation you've seen in calculus, right? So I'm going to do this for sine of z, okay? So let w equal to inverse sine of z. So that means sine of w is equal to z. Okay. And so we're going to suppose like w is a function of z, right? And we're just going to take the derivative of both sides. So the derivative with respect to z of this equation, right? Well, this would be cosine of w times dw dz equals to 1, right? And so dw dz is equal to 1 divided by cosine of w, right? And this trig identity for complex numbers would work. Cosine squared of z plus sine squared of z is 1. It's very easy to show it, right? But this is true, okay? Just use the definitions for cosine of z and sine of z to show it, right? So what that means is that dw dz, so, okay, this would equal to 1 over 1 minus sine of w to the 1/2 power. Again, we don't incorporate plus or minus because this quantity itself would bring out 2 distinct roots to begin with, right? So w is inverse sine of z, and then z is just w, so this is squared. Oops. This here is squared, 1 minus sine squared of w. So d dz of inverse sine of z, this equals to 1 over 1 minus z squared to the 1/2 power. Okay, 1 minus z squared to the 1/2 power. Okay. So that's how we would get that as the derivative. Oops. Okay. So you can do the same trick for showing the derivatives for inverse cosine and inverse tangent, right? So let's go over some examples. So use use the principal branch for the square root function, which is indicated here, right? And the principal branch of ln of z to find inverse sine of z at z equals 1/2 I. And also the derivative. So work out this problem and try to see what you come up with as a solution. Okay. All right. So I assumed you worked on this example. Let's go over it. Okay. So the principal branch for the logarithm is theta has to be in between minus pi and pi, right? So without further ado, let's look at how we would compute inverse sine of 1/2 times I. Okay, so by definition, this equals to minus I times capital natural log of I times 1/2 I plus 1 minus 1/2 I squared to the 1/2 power. Okay, so this equals to minus I times the capital logarithm of minus 1/2 plus so this is 1 minus, so 1 minus negative 1/4 to the 1/2 power. Okay. All right. So this equals to minus I times capital natural log of minus 1/2. This is 1 plus 1/4, so that's 5/4. So basically compute the square root of 5/4. All right. So 5/4, we want that to be, so we want our angle to be minus pi over 2 and up to pi over 2 radians, right? So it's literally just 5/4 to the 1/2 times cosine of 0 plus 2 pi k over n. So over 2, excuse me. Right. And so we'll just have square root of 5 over 2, right? So pretty straightforward. So this equals to, so therefore we'll have minus I, so this equals to minus I times capital natural log of, so I'll write this as root 5 minus 1 over 2, right? So this is real, this is a real number, so its angle is 0. So basically this equals to minus I times log base E of this quantity, right? The absolute value number is that number plus I times theta, but theta is 0. So we'll have this quantity here as our answer. Okay. So hopefully that works out. Also, let's look at the hyperbolic trig functions. Their derivatives and inverse functions. So it's going to be analogous to the rules to compute the derivatives and inverses of hyperbolic trig functions in calculus. All right, so it's going to be the same thing, right? Okay, so we looked at what the definition of hyperbolic sine of z is. So it's e to the z minus e to the minus z over 2. Hyperbolic cosine of z. This is e to the z plus e to the minus z over 2. And then hyperbolic tangent of z. This equals to hyperbolic sine z divided by hyperbolic cosine of z, right? Okay. And the derivatives are the derivatives of hyperbolic sine of z. So just use differentiation of sum or differences of complex functions, and you'll get hyperbolic cosine z, right? The derivative of hyperbolic cosine, this will be equal to hyperbolic sine z. And the derivative of hyperbolic tangent is equal to hyperbolic secant. Okay. Hyperbolic secant squared of z, right? And so the inverse functions for hyperbolic sine, cosine, and tangent are similar to what you've seen in calculus, right? So this equals to the natural log of z plus z squared plus 1 to the 1/2 power. Okay. Inverse hyperbolic cosine of z is equal to the natural log of z plus z squared minus 1 to the 1/2 power. And inverse hyperbolic tangent is equals to 1/2 times the natural log of 1 plus z divided by 1 minus z. Okay. And then finally, the derivatives are for the inverse functions are the same, right? So this equals to 1 over z squared minus 1 to the 1/2 power. The derivative of hyperbolic cosine inverse of z, this equals to 1 over z squared. Oh, this is plus 1, minus 1 to the 1/2. I meant plus 1 here. And then the derivative of inverse hyperbolic tangent. This is 1 divided by 1 minus z squared. Okay. All right. So those are the various rules for hyperbolic trig functions. So let's go over one more example. So find, let's say, hyperbolic cosine inverse of z and the derivative of inverse hyperbolic cosine of z. And z is equal to minus I. Use the branch for z to the 1/2, where minus 2 pi, where theta is in between minus 2 pi and 0, and the principal branch for ln of z. Okay? So I want you to pause the video and work on this example on your own for a bit. Okay? All right, so I assumed you worked on this example. And let's actually compute on what this equals to. All right, so we have that z is equal to I. So first, let's look at what hyperbolic inverse cosine of minus I equals to, right? So by definition, this equals to the, well, capital natural log of, in this case, it's minus I plus, so minus I squared minus 1 to the 1/2 power, okay? And so this equals to capital ln of minus I. So I squared is -1, so that would be minus 2 to the 1/2 power, okay? So we want to use the branch where theta is in between minus 2 pi and 0. So essentially we are going clockwise around that way, right? So the point -2 would be here, but since our theta is in between minus 2 pi and 0, the theta for this number is minus pi, right? So, okay, so the square root of 2, minus 2, so this would equal to, so the modulus of 2 to the 1/2, so 2 to the 1/2 power times cosine of minus pi plus 2 pi k over n. Okay, so plus I times sine of minus pi plus 2 pi k over n. So in this case, n is 2, and then k is equal to 0, and then 1. So these n's should be 2, okay? All right. So this equals to 2 to the 1/2 times cosine of minus pi over 2, and then plus I times sine of minus pi over 2. That's where k is 0. And then when k is 1, we'll have 2 to the 1/2 of cosine of pi over 2 plus I times sine of pi over 2, right? Cosine of pi over 2, that's 0. Sine of pi over 2 is -1. So when k is 0, we would have 2 to the 1/2 times minus I, right? And this is equal to 2 to the 1/2 times I. Since our range is in between Minus 2 pi and 0, these are, so these angles would be minus 3 pi over 2. Okay? So our roots are along these axes. So it's along these points here and here, right? But the so theta over 2, this angle must be in between minus pi and 0, right? So in this case, we want to use this number right here, right? This number right here. Minus pi over 2 is in that range, so that's good to go. All right, so we have our value, and all we have to do is compute the natural log of that. So we have to compute, so hyperbolic cosine of minus I, this equals to capital Ln of minus I. So minus 2 to the 1/2, that was 2 to the 1/2 times minus I, right? Minus I. And so this equals to capital Ln of minus I times 1 plus root 2. Okay? 1 plus root 2. And by definition, this equals to log base E of, in this case, 1 plus root 2 plus I times theta. Theta has to be in between minus pi and pi. That's the principal branch. So this value here is in the quadrantial angle where it's pi over 2. So in this case, it's plus I times pi over 2. And that is your answer. Okay. So that's how you do that example. Hopefully this makes sense. So here's some problems for you to check for comprehension. I hope these problems are working out well for you. So 2, 6, 8, 10, 13, 16, and that's it. Okay. So next we're going to get into integration this time in the complex plane. So we're going to get into what it means to integrate complex functions. So stay tuned for that. Hopefully you're having a great time with this class so far. If you have questions, always let me know by emailing me or shooting out questions in the comments. Okay. But I will see you all in the next video. Take care.